Yeah.
For the afternoon. So our first speaker this afternoon is Margaret Symington from Mercer University to tell us about beyond reflexivity symplectically.
All right, so everybody's thanking the organizers, but we all have to thank them because this has just been great so far, and it'll continue to be great. So thank you so much for the opportunity to come partake in the symposium. And this talk is probably a little different from some of the others. I think they, had like a whole lot of results, and this will have, some little results, but the invitation included an invitation to talk about things in progress. So this is a project that is, I think, really at its beginning still and is very dynamically in progress. But I hope to share some perspective, and hopefully there'll be something for everybody to enjoy. So the goal here ultimately is a symplectic one. I'm interested in understanding Lagrangian fibrations of K3 surfaces. So in the talk, first I'll remind people what a K3 surface is, explain a little bit about the Lagrangian fibrations, and then, hopefully through the talk convey a little bit what I mean by understand, because that means different things to different people. But for me, it is pretty tactile, and it means that I can actually get in and sort of see and feel these things. And for that, polytopes help a lot. So that's why it's ultimately going to be about polytopes by the time we get further in. So a K3 surface is a simply connected compact complex surface that has a nowhere vanishing holomorphic form on it. So it's the smallest interesting Calabi-Yau manifold. It's the only one in complex dimension 2. And if you like it this way, you can think of it as a degree 4 hypersurface in CP3, if that pleases you. So that's certainly a very nice presentation. I tend to think of things more topologically, so I'm very happy to think of it as a fibration over the sphere, and it has 24 singular fibers. And you could think of it as having symplectic fibers, or as Chris was talking about, we're in this happy situation with a K3 surface that there's a hyperkähler twist that you can do with certain metrics, and you can turn the holomorphic fibration into a Lagrangian one. And it's the same vibration topologically. So I'll be talking about the Lagrangian ones, but around a fiber, there is some monodromy in the torus fibers, and the fibers are these pinched tori. They are the ones that are the well, I guess, yes, that were appearing in the spherical pendulum that Chris was telling us about. So that's the K3 surface. It's beautiful and wonderful. And topologically, there's one. From a complex algebraic geometry standpoint, there are many. And symplectically, it's, you can vary the cohomology class. But if you really want something, more detailed, it's nice to have a fibration, and especially a Lagrangian one. But if you're thinking about symplectic fibrations, then you can build your K3 as a fiber sum, really as a symplectic sum of two copies of the elliptic surface E1, which has 12 singular fibers, E1, E2, E3, E4. You can just take fiber sums and get, n copies, n12 n copies of E1 that are glued together along a torus, just doing a symplectic sum. And E1 is CP2 blown up at 9 points. So that's something really nice. Now, you also may want to do this in a Lagrangian fibration. And if you do that, okay, where are you going to find Lagrangian fibration of CP2 blown up at 9 points? Well, it's a toric CP2 that has been blown up in a toric way 9 times. So you could do that, and that's a picture of it. And I drew the CP2 blown up 3 times in blue so that you could sort of see it, and then 6 more times to get the red. And so then the question is, where's the key to take the fiber sum? Because you're going to need a symplectic torus, and where it should be is in the pre-image of the boundary. But the pre-image of the boundary is a union of a whole bunch of spheres that are all intersecting very nicely, but you have to, resolve that. So, well, that's when the sort of starts to get a little more interesting. In general, for a Lagrangian fibration, it's very rigid, because whatever is happening upstairs in the fiber is reflected downstairs in the base. And that gives you an integral affine structure on the base. That's where it comes from. And so what this tells you is that if you want to study a Lagrangian fibration of the K3 surface, you can learn a huge amount about it just by looking at the base of the fibration, because that sphere in the base has a geometry on it in which the structure group is GLNZ, semi-direct product with Rn. So that's the affine, or AGLNZ. So I need to tell you, what happens. So upstairs, the monodromy was, you had a monodromy matrix upstairs around the torus. And so downstairs, if you go around the image of a singular fiber, you're going to get some holonomy in the integral affine structure. And when you look at it, you have to make, okay, so if you want to understand the structure, you can, make a cut, and then you have a simply connected piece. Okay, so that just looks like it has maybe the standard standard integral affine structure on it. The holonomy matrix has an eigenvector. So if you cut along the direction of the eigenvector, okay, then the image downstairs that you have of your your neighborhood and its integral affine neighborhood surjects onto R2 with its standard integral affine structure. And that's because the holonomy, as you go around, is a shear, okay, and it's a shear along that direction. If you cut it open in a different direction, then your picture will look different, and it's the same neighborhood. There's nothing different. You're just seeing a different picture of it. So if you have one of these singularities, you have the singular point, but it has in its data some eigendirection that it knows about. And so that's sort of a piece of the data that you want to recognize. So if you are wanting, say, to use this CP2 that was blown up at 9 points to build yourself say the integral affine base of a Lagrangian-fibered K3 to then clump 2 of them together, you want to make use of an almost toric fibration of your blown up CP2. And so rather than doing just toric blowups, you can do nodal trades and almost toric blowups, and those introduce the singular fibers. And so you can trade what's called an elliptic singular fiber, or the point that's in the image of the moment map at a vertex. And you can trade that singular point for the singular point in the pinched torus. Okay. And, or you can blow up. This should look sort of like a blow up, because a blow up, what do? You take out a triangle, right? And so we took out a triangle. It just looks a little different and you have to, glue it back together again, but that's the almost toric blow up. So if you're going to blow up like that, you have lots of flexibility as to how you want to blow up your CP2. So there's a CP2 that has actually in the pre-image of the boundary now, the holonomy takes this boundary curve and it looks like a corner, but there's no corner there. Sitting over this point, there's a circle. Okay? There's no point, and it just goes around. The holonomy takes you around that corner. So there is a symplectic torus sitting above that red curve. And so it's ready and waiting to glue to another Lagrangian-fibered or almost toric fibered CP2 blown up at 9 points. And I could make any kind of blow-ups I want as long as basically the length of the two red curves on my two guys match, then I can glue them together. So that's nice. I can build lots of them. And you can ask when I do this, I'm doing it really on the complement of the nodes, but there's no obstruction to filling in the singular fiber. You can just put it in. So you do all this work on the integral affine structure on the complement of the singular fibers, on the complement of the nodes. And then you can ask yourself, if you do want to look just at the base and understand your fibration from the base, what are you learning and what are you missing? You can see the cohomology class of the symplectic form, and you can read off a lot of data from the integral affine structure, because there are, at least in rational directions, integral affine lengths that you can measure. There are measurements that you can make that tell you something about relative positions of singular fibers. There's the data of the directions that are invariant at each node. So there's quite a bit of data. The things that are not there is when you come to fill in the torus fiber, the singular fibers, they have invariants that are very fine. Mungok, was described the Taylor series invariant that is, determines sort of in a fine way how that singular fiber gets glued in. But I'm not going to keep track of that. There's also can be a churn class, and you'd have to think about how those interact, and there might be, something you could look at there. But the integral affine structure itself will tell you a lot. So that's, I'm going to sort of forget about the 4-manifold upstairs and just look at this 2-manifold with its integral affine structure. And well, that's already significant because there's a 44-dimensional space of integral affine structures on the complement of 24 points on S2. So I'm not studying that space. I'm not trying to compactify it. I'm not trying to do anything with it. I just want to know what these things look like, really. And so I'm going to focus on examples that have nice extra structure. And so that's where the polytopes come in. And the polytopes really came onto the scene from mirror symmetry, because in the Strominger-Zaslow sort of perspective on mirror symmetry, the idea was that you would have these mirror pairs of Calabi-Yau manifolds, and they would have special Lagrangian fibrations, but if that's too difficult, then at least Lagrangian fibrations that are dual to each other. And in dimension 2, the dual is, again, a K3 surface, and so you get pairs of induced integral affine structures on S2. Are there any questions yet? So in 94, Batyrov sort of proposed that and found a way to sort of describe, I guess, find Calabi-Yau pairs, do mirror pairs as hypersurfaces in the toric varieties defined by lattice polytopes that are reflexive. So if you have a polytope, you can look at its polar dual. Okay. And when you find its polar dual, if it's again a lattice polytope, then that's what it means to be reflexive. And I'll give a more geometric and I think accessible definition than that one in a little bit. But so these are polytopes with their vertices on lattice points they're in Zn inside of Rn. And so inside of the sort of toric varieties defined by reflexive polytopes, he found these families of Calabi-Yau manifolds that could be thought of as limiting onto their boundaries. Okay. And I think maybe I didn't put it in the slide, but you can take the boundary inside of, say, well, we can do it in CP3, so we're working with the K3 surface. You could take x1, x0, x1, x2, x3 equals 0, and that is the union of the boundary, right? That's the boundary of the polytope. And you could perturb this plus any smooth Q, any other degree 4 polynomial you want. But in particular, you could, if you want to pick the Fermat, and so you could look at that. If you look at that family, that's the kind of thing that was being examined. And this has generated a huge amount of work, many different perspectives. So that's a little bit of a list. I included at the end here some that's ongoing of Chakravarti and Groman trying to, one of the complicated things is if you want to kind of pull back from the pre-image of the boundary of the polytope, which is a union of toric varieties, to something smooth, right? Inside this kind of family that's degenerating, and you want to pull the Lagrangian fibration back. Ron had an approach to that, and they're working out some interesting details on that. So if you are interested in more sophisticated and detailed things, you can look there. But for the algebraic geometers, ultimately, if you take a dual reflexive polytopes, these give you mirror Lagrangian-fibered Calabi-Yau manifolds. If you don't care about the algebraic geometry and you just want Lagrangian fibrations, then you could do this. You do the same thing, but what polytopes should you be looking at? So the symplectic world is softer than the algebraic one. We should have more polytopes, and which I don't know what it means to say which Lagrangian-fibered K3s we'll get, but we can certainly ask which polytopes can come. So I'm going to be looking at polytopes that support an integral affine structure. So first thing to notice is that the boundary of a polytope, if it's a three-dimensional polytope, it is a sphere. Right? I mean, topologically, that's a sphere. So that's the base of a fibration. And in what sense could it be supporting an integral affine structure? Well, it is when I put the singular fibers on the edges, because remember, singular fibers have a direction that they know about, and that direction is the direction given by the edge. So it's natural to sort of have them sit there, and then the facet of a polytope should be getting the integral affine structure just from inclusion in R3 from the standard integral affine structure. And so that's, I'm denoting by A0, and A is the induced integral affine structure on the polytope. And so, an integral affine structure is flat. Last time I checked, the sphere is not flat, right? And these points are not cone points. The holonomy around them is a shear. So I don't know about you, but for me, that gave me pause. Like, how am I getting the curvature on the sphere from these shears? And so I was very happy when I realized that, and I'll show you a picture that helped me understand it. And then ultimately, they're gonna have to be 24 nodes, they're gonna have to sit on the edges, and they don't just sit randomly, they sit according to the geometry of the polytope. And then if all of that is sort of working together, you'll say that that polytope is supporting an integral affine structure. It's somehow adapted to the polytope. So how do nodes introduce curvature? So that's a strip. Okay, so the little green edges on that side, I'm going to just make myself a little, cylinder, right? Glue them together. But I have introduced some singular fibers. So I'm going to think of this as a Lagrangian fibration over that strip, but with a nodal fiber or singular fiber over each one of those stars. And the invariant direction needs to be along that central line. That's the invariant direction. And so that means that when I cut, the shear is in that direction, right? And so that shearing will glue any one of those little blue dotted edges to the other one. And so, well, when you do that gluing, what happens by the shear? Well, you do that to your cylinder and glue your cylinder together, and yeah, that's curved. So I thought that was nice. But I can also, you're trying to understand these things from the polytopes. You want to understand it naively. The algebraic geometers, I take the cube, and it's a reflexive polytope. And if you look at the data, we'll see how to do that in a minute, but it'll get 2 nodes on each of its edges. And so if you want to see, the sort of how to glue this thing together, or the flat structure, you can basically take this apart as if it was a box that was gift wrapped for you. And so you can just cut, say, along that green cut, to cut it in half. And then you need to cut open, okay, somehow so I've taken the front half of it, and now I need to get myself something simply connected. So I'm going to make a cut there and a cut there, and I make the various, and a little cut right there. And when I open it out and lay it out, that's what it looks like. Yeah.
I'm just confused about, so you're talking about this is 2 real dimensions?
So this is okay, so
So
the manifold is CP1 cross CP1 cross CP1, but I'm looking at the boundary.
So because essentially you're trying to describe the Lagrangian-fibered of something 4-dimensional or 6-dimensional?
4-dimensional, because it's just over the boundary.
I see. So
everything is over the boundary. So here, that's why I'm sort of unwrapping this gift wrapped box, right? So the box is the polytope, and it contains the data for, well, that was one of the things I wanted to understand, was how does it tell you how to unfold, right? I mean,
so you're looking at a Lagrange, so 4-dimensional manifold, singular Lagrangian-fibered, and the base space is topologically a 2-dimensional sphere. Thank you.
that's where we're at. Everybody good?
And so here you don't do the smoothing of this thing, just something over the whole boundary.
Okay, so when I unwrap this correctly, okay,
Uh-huh.
so that doesn't look like a smooth point, but it is a smooth point, okay? And that's how it glues together.
Because of the integral affine structure.
The integral affine structure. And so that will be one of the questions is, how do you get the integral affine structure on a vertex? Because there's nothing, that's a smooth point. Okay. The only singular points are at the nodes where we have a shear in the holonomy around it. Okay. All right. So, anyway, this one, without knowing too much, you can just sort of, lay it out, and you can actually see that this is an S2 cross S2, like if you sort of look at that green boundary, right, that has been blown up a bunch of times, and just enough times to get you into the same manifold as CP2 blown up 9 times. So that is ready to glue to the other back half the same way. And you could unwrap it differently so that you get a coordinate chart on the whole thing. And I don't know, I'm just showing you this because I think those pictures are nice and I like to see them. I like to see integral, that is a coordinate chart for the whole integral affine structure on that, that's supported by that polytope. Okay, so here's just some other pictures. These are, well, these two are Delzant. That one is not Delzant, but it's really simple. And it wasn't hard to figure out how many nodes should go on each edge. And I'll tell you how that goes. And just look at a few more pictures. So if we focus a little bit on Delzant polytopes, you know, symplectically, that's a natural place to look for the base of a fibration. And you could ask which Delzant polytopes are going to support an integral affine structure. And so in a recent paper by Godinho, Lindsay, and Sabatini, they simply have a nice language. They call the integral of the first Chern class of the tangent bundle the magnitude of an edge. So so this is of the in the six manifold. So you know you have your three-dimensional polytope. It gives you a six manifold. You have C1 of the tangent bundle of the six manifold. The edge, the preimage is a two-sphere, and so you can integrate the first Chern class over that. But if you want to do that more, you can make that calculation just in the polytope. You can simply look at the edge and look at each of its facets, and you can just sort of calculate the contraction rate. This is an integral affine contraction rate, and in each of the neighboring facets. And that's exactly the same thing as calculating the self-intersection of that sphere inside the four manifold of that facet. So whether you like to think about self-intersection numbers or contraction rates on the polytope or the integral of the homology class, is all of those things plus two, and that plus two is from the so these are the C1 and the C2 are for that edge going into the normal bundle, and then in each of those neighboring facets, and the two is for the tangent bundle of the sphere. So it's when you start looking at this, Delzant polytopes are really nice because there's really only one way to put that integral affine structure on the vertex. It's very rigid, and so you can look at it, and so Liat and I it was on the slide. So Liat Kessler is my collaborator on this. You can look at this and see that if you have a Delzant polytope, as long as each edge of the polytope has non-negative magnitude, then the magnitude is the number of nodes it needs on the edge, and you have the base of an integral. You have it supports an integral affine structure. And so this takes you outside of the world of reflexive polytopes, and it's nice, sort of a clean result. So sort of what it looks like is the magnitude is kind of how not flat the neighborhood of the edge is, because if you project down sort of a neighborhood of a vertex, it has to look like one of these pictures of, I mean, there's really only, it's very, very rigid how the three sort of neighborhoods in those three neighboring facets come together. If they're going to be Delzant, then, well, you have some choices, but if you make a change, if I change my choice of how to map the vertex down there, it will change sort of whether I'm shearing down on this edge or on sort of in the lower part or in the upper part. And ultimately, those, four nodes are telling you, oh, this is going to not be flat. It has to get folded up somewhat. Okay, so just some Delzant examples. If you take a simplex, not necessarily a standard one, so I'm letting the facets look like Hirsebruch surfaces, say. So as polygons, they'll have contraction rates 0, -k, 0, and k as you go around. So I've lopped off the summit of the simplex, and it's that top edge that constrains whether this can support an integral affine structure or not. Because I had to have non-negative magnitude, and if you calculate the magnitude of that edge at the top, it turns out to be 3 minus k. So I have to have that k is less than or equal to 3. And if k is less than 3, and 3 would give me 0 magnitude. If k is less than 3, then it's not hard to see that you can, choose the lengths of this so that the polytope is actually reflexive. Okay, so it is in fact monotone then when the magnitude is positive. It's also nice. I mean, just one more set of examples are fun to work out. If you just take a prism, just take a Delzant polygon, cross an interval, and ask which ones of these will support an integral affine structure, then they have to have 9 or fewer sides to them, those polygons, because they have to have a contraction rate, or the spheres have to have self-intersection at least -2. And that's because in the other direction, in the vertical direction, it's a prism. And so the self-intersection or the contraction rate is 0, and 0 plus 2, -2 plus 2 is 0. So I have to have at least -2. And so there are 16 of those. If you restrict to, if you want this to be reflexive, then that Delzant polygon will have to have the contraction rates being at least -1, and there'll just be 5 Delzant polytopes that you can do that with. So you see sort of what you see in the Delzant case is that beyond the reflexive ones, you go a little bit, not dramatically, but you go a little bit, you loosened it up a little bit. So here's the status. What you have is that if you have a reflexive polytope, the algebraic geometers tell you that the integral affine structure is there on that. The polytope supports an integral affine structure. And we have a condition for Delzant ones. And if a polytope is reflexive in Delzant, then that's those are monotone manifolds. But so little question, the next question is, well, what about outside of that? Okay, what other polytopes could you have that will support an integral affine structure? So coming back to this list, okay, yeah, the boundary of the sphere and blah, 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 blah. Where was the reflexivity showing up in this? And the only place that reflexivity was showing up was, in this geometry of the polytope and how it was going to tell us how many nodes were on there. So it's just in that last line that reflexivity was playing a role. So what I want to do is look a little more closely at the reflexive condition to understand it better and then see how to go past it. So in a reflexive polytope, it's helpful to rephrase the reflexivity condition, and this is completely standard. This is not mine. You can look at lots of sources on this. So if I have a point in Rn and a hyperplane, I take its primitive integral normal vector, and then I take the inner product of, so I have a point in the hyperplane, take a vector from the point to the hyperplane, and take its inner product with that primitive integral normal vector, and that is the integral affine distance of that point from that hyperplane. If your point is a lattice point, then this would be called the lattice distance, but I'm working with Delzant polytopes, so I don't want to really restrict to lattice points. In this phrasing, and I also don't really want the reflexive polytopes, the description in terms of polar duals the polytope has a single integral point on its interior, and that's the origin. But I'm just talking about the geometry of these polytopes. I don't care where it sits. So, and this is also described similarly elsewhere. So you can say a rational, if you just take a rational polytope, you can say it's reflexive if there's some point on the interior so that every facet is integral affine distance 1 away. And that makes it reflexive. So that's a much more natural definition from a geometric standpoint. And then that point is called the center of reflexivity for delta, for the polytope. Okay, so what I claim is that you can think about reflexivity locally. I mean, it's just about facets being unit distance away from some point, unit integral affine distance away. So if I have a vertex, then I have the center of reflexivity and the vertex, and I take a vector primitive, I take the vector between them, okay? So from the point to the vertex. So that's to a point that is common to all of those facets. And if I quotient out by the by this vector, if it's, I need it, let me see. So, right, so I have that vector and I want to know, what do I want to do? I want a projection of all of my facets in a common way down to some plane, right? And that's going to just be a quotient. So I'm going to quotient by this vector, and I need, in order to have an integral, not just an isomorphism, but an integral, an integral affine map, I need that the inner product of the normal vectors to the facets with this vector that goes from my special point to the vertex be 1. That's just saying that from the perspective of reflexivity, when you're trying to decide if your polytope is reflexive or not, you start looking at it and it's like, oh, okay, I've got a vertex and I check the conditions on the facets that meet at that vertex, and I check, do I have the reflexivity condition? And if I do, then what that tells me is that I have a coherent way to make an integral affine isomorphism from the facets down to the quotient.
So if your polytope is simple, then this is always toward each vertex, or?
If the polytope is simple, yes. If it's Delzant, yes. Simple, no.
So
No, it needs to be, if it's Delzant, it'll be true.
I see. So simple is not enough.
Simple is not enough. It could be locally reflexive, and it's a weaker condition.
No, I'm asking about.
I know this condition, but if you make it
Just
simple,
vertex,
it's
just
still
a
not
vertex.
enough. It's not quite enough. I mean, simple is just that there's 3 meeting there, and that's not going to give you this condition.
No, but you need to choose okay.
Yeah, but there's not a common point. There has to be a common point that's working for all 3, because I mean, the idea is that I'm patching things together, so I have to have some coherent thing for all the facets that are meeting. So my claim is that one way to think about what reflexivity gives you is from the perspective of a vertex and trying to put an integral affine structure on the neighborhood of a node. Reflexivity at that vertex does the job. But now you've got to paste things together and you want to have an integral affine structure on the neighborhood of an edge. And you need to be able to put it in nodes, which only introduce sort of positive curvature. And so, way back when, Batyrov and Dice proved how to calculate the number of nodes on an edge in a reflexive polytope. And so it was and for them, these are lattice polytopes, so they're carrying sort of the integral affine topological information, I guess. So you take the length of the edge, and then you take its polar dual of that edge and its length. You take the product, and that's the number of nodes that guy gets. So if you're working with a Delzant polytope, okay, the length you can make it any length you want, right? But let's just say a polytope is reflexive at an edge, not just at a vertex, but an edge, if there's a common point that is lattice distance 1 away from all the facets that have non-empty intersection with that edge. And it's basically saying it's also for that, to the two vertices together. And that point will be the center of reflexivity. And if you can do that, then, well, that's how you decide for a reflexive polytope how many nodes it gets, but it's a local condition again. And as a local condition, well, if I'm working in a Delzant polytope, I can rescale the polytope and make that edge any length I want. So if I can rescale the edge so that there is such a point, then I know how many nodes it should get. It's given to me by the algebraic geometry. Okay, so I have this sort of reflexivity at the edge. And again, the Delzant polytope doesn't see the scaling, but just as we saw in the Delzant case, this really just has to do with the contraction rates in the neighboring facets. It's just now we have a singular variety, maybe, or this is not a polytope that corresponds to a smooth manifold, so it's a little trickier. We have to appeal to those. So if you have sort of up to scaling reflexivity at the edge, then I know how many nodes it gets, okay? And it could be part of, I know how to put my integral affine structure there. But there's also another case, and this is the case that corresponds to when you have 0 for the number of nodes. And that's if this doesn't happen, but if you collapse the edge and let it become a vertex, and you look at the cone that you get, if that is a cone that has a point making this cone reflexive at the vertex, then that edge gets 0 nodes, and it's fine. And you know how to put the integral affine structure on it. So you're getting a semi-local condition on your polytope. And so the theorem is, well, so the theorem is that if you have a polytope that satisfies this kind of condition, one or the other at every edge, then it supports an integral affine structure. So here's an example where you take something that's not Delzant and not reflexive. So you start with a reflexive polytope. So the octagon is a reflexive polytope. And you can basically pull it apart at the north and south poles. If you pull it apart, then that's exactly this kind of collapsing I was talking about. And so this will get 0 nodes on each of those edges. And so this will have an integral affine structure on it, but it's not Delzant because these vertices here are not Delzant, and it's not reflexive because it has these edges that have 0 nodes on them. And so it's an example that is outside of both the Delzant and the reflexive world. So you sort of now have a picture of, I don't know, how many? I have no idea how many. So there are, thanks to Cruiser and Skarka, there are 4,319 reflexive polytopes in dimension 3. So, I mean, this is like ridiculous in terms of a 44-dimensional thing, but at least, we got some nice guys, right? So there's 4,319 here. I think there's 19, I think there's 18 in here. What we conjecture is that there's a finite number of Delzant ones. It's a pretty strict condition on the Delzant ones. But also we conjecture that there's also a finite number that satisfy the condition that it gets imposed for the numbers of nodes being positive or 0. So those are the two conjectures we have. And I think we're probably pretty close to proving the first one. The second one, I think, is pretty interesting. I don't really understand the edges that have 0 nodes on them. I think they are constrained. I think it's still pretty constrained. We don't understand that picture entirely yet. the, what are some of the things that you see in these pictures? So if you have nodes that are lying on a single edge, they all share that same eigendirection. That means the fibers upstairs all have the same eigenvector of their monodromy around them, which means that they really live in a semi-toric neighborhood. So you have a whole bunch, however many that you line them all up, and they all are in there. And I think it's interesting to ask what's the maximum number of nodes that you could get? Oh, that's mistyped, sorry. How many nodes on an edge, okay, on a single edge can you get? So you can, if you're not worried about it having a coming from a polyhedron, you can arrange for 18 nodes to lie on a single line in your base. You can arrange for that, but you can't go over that for topological reasons. And we have examples where you can get 6 on an edge in a polytope, but I have no idea where in between. And then you could just ask more generally, what kind of constraints are there in terms of how these 24 nodes are sprinkled around on edges? What kind of partitions can you get? But there's even something more fundamental that I think is interesting, but I don't have any intuition for. I mean, I could guess, but it would just be a guess. I hand you 2 integral affine spheres, and they are each supported by 2 different polytopes. Well, maybe maybe they're isomorphic integral affine structures. It's just I arranged the polytopes differently. It's not obvious that the polytope is an invariant. It'd be nice if it is, but that's not clear to me. And I think that's interesting. So that's it. There's lots of questions that you can ask. You can start, if you really want to just sort of live in these integral affine structures, you just put yourself down at a node and set yourself off going in that direction and ask what happens and where you end up, or what happens to your path. And it's highly sensitive to the arrangements in there and the dynamics. I mean, there's lots and lots of I think it's a really cool sphere. So I'll stop there. More than 10 minutes on your day.
Questions?
Actually, in the previous slide, you said you can determine the homology class of the symmetric form.
Yeah.
K3. So can you say something more about that?
Yeah, sure. So I didn't say I could necessarily do it so easily, but the nodes, if you think about how it gets, let me go back up to a non-polyhedral picture, but I could always unfold any polyhedral one down to the plane. So I can see generators of H2 in this picture, okay? And I can measure the length, the integral affine length of the curves over which the generators of H2 live. So I can calculate.
Yeah.
And then,
But this is for E1.
well, no, it got glued to another one. So that was an E2. Now this is special. I mean, this is another thing that's interesting, is this is special because there is, when you build it this way, there's a line, right? There's a geodesic, an integral affine geodesic that splits your integral affine sphere. And there's no reason for that to exist in general. So those are special. But no, when I say I meant H2 of the K3 surface. So these curves some of them will run from this half into the other half. So there's 2 of these that are glued together. So I'm not saying that I know how to read it. I'm just saying that the nodes and their relative positions carry that information. But if I cut it open I could probably guess in principle, you could figure it out. Yeah,
Is there any intuition as for why that number was so oddly precise, 4,319?
I don't think so. I mean, they count, they count, I mean, the numbers go up dramatically, so when you go up to dimension 4, it's in the millions. Yeah, Cruiser and Starker they just, you know, developed an algorithm to run through and build these things and count them. So I don't think it was a theoretical count, it was a brute force count. Is my understanding, I mean, you know, from their algorithm. Yeah, Mohan.
When you construct one of these integral affine structures on polytope, is there a unique one or is there a moduli? Can you perform them at all?
So, right, so there's one thing they can do is the nodes can slide freely on the edges because that's the Lagrangian direction, so there's nothing happening there.
Does that,
Now, and, okay, you could want to push one of them off, right? But you can't do that independent of the others. And so that's one of the things that I don't really understand is, okay, suppose I want this one to move this way, right? Now I can understand it better in this kind of a picture because in the plane, well, when I have control, like when I have it split as a sum of two E1s, I can see it better, right? But in general, yeah, if I want to perturb one some way, I don't really know. There's another thing that I'd like to understand, but I'm not sure it's the right way to think about it. But if you go back to the cube, and by the way, I had undergraduates helping me. I mean, I'm really a know-nothing. I mean, like working on this project, I didn't know anything and started out literally with first understanding the thing about the curvature. And then anyway, it's been a slow process, but going to the cube. Okay, so you take the cube and we have, these two nodes can slide here. Okay. Well, they're actually, if you follow this line, the integral affine line goes up the diagonal and back around. So there are actually 4 nodes that live on that guy. And you could ask, well, what happens if you push this along past the corner? Okay. And it would be really nice if, you got another polytope, but I'm not sure you get another polytope. You may just be in a non-polytope integral affine structure. And so I think that one thing that could be cool is, okay, I mean, again, these are probably a finite number of guys sprinkled around in this huge space, but maybe you could understand how to move between them by, like I mean, another perspective on this is, the polytopes, this presentation knows where the nodes are. But you could just say, let's go back to the case of just CP3, okay, and say that cortex in CP3. Okay, so there are 4 nodes on each edge, and that's because if it's degree 4, really. And so I could think of this as wanting to take 4 copies of CP2 and glue them together, right? That's what I want to do. And I have to blow up a certain number of times in order to be able to do it. And I was just telling John, well, that's what I did in my thesis. This is a 3-fold symplectic sum. You just, there's going to be 3 of these guys that are glued together, and you have to blow up a certain number of times. And I could blow up, twice on this edge and twice on this edge. And now my nodes are on the interior. And in fact, for those who, the group that I was saying was working on trying to recover the Lagrangian fibrations on smooth members of a family that is degenerating, say, to that boundary. They're thinking of those as living inside the polytope, right? So you could maybe the right way to move between the polytopes is to go to these that don't really belong to the polytope, but they're still kind of there. You can still kind of see them on the polytope. So maybe the polytope is still helpful. Sorry, that was maybe kind of a long answer, but. Other
Maybe
questions?
The interior, that can nothing be in the interior of the,
Interior of the facets, yes, if you let go of,
like the,
I mean, if it's no longer, I would have, no longer say that the. I mean, the polytope is no longer telling you so much, right? It's maybe telling you something, so I guess. It depends how much information you want to retain.
or like in the interior of the whole, like,
Of the six manifold, no,
okay, they are not allowed.
they don't have any meaning. I mean, the four manifold lives over, the four manifold. Is really. I mean, I'm smoothing the, that boundary, right?
Right,
But, I'm just doing it by gluing things together. I'm not smoothing anything. I'm just symplectically gluing these
okay.
Lagrangian fibrations together.
okay.
Well, yeah, I should say these almost toric fibrations. So I'm just gluing almost toric vibrations together.
Okay, sorry, question.
So what about integral Raman structure on RGT with 12?
Oh, yeah, you could just quotient, there's just 12 of them. So well, you'd have to have a non-orientable polytope. So,
What's the expected?
I mean, the base is RP2. And it has 12, and it has, 12 nodes on it. So yeah, you can study integral affine structures on RP2 with 12 nodes.
So the expected dimension be 22? Probably.
Roughly, I guess. I mean, I'd have to think about it, yeah, but something like that. Might not be exactly that, but close. Other questions?
Okay, let's think like this. So coffee break upstairs, and then we'll return here at